Point cloud pre-training with natural 3D structures. Recently, 2D image recognition methods have shown excellent performance. There are two major reasons for the significant improvement in performance. The first factor is the proposed feature extraction method using CNNs. The second factor is the proposed pre-training model using ImageNet and JFT-300M. Supervised pre-training is known to improve recognition performance in downstream tasks, prevent overfitting, and speed up the training time. Furthermore, since the advance of 2D vision, 3D object recognition using 3D point clouds has recently been actively studied in 3D vision. 3D point clouds can represent fine-grained geometric structures such as 3D objects and 3D scenes in the real world. However, that progress has been somewhat slower than 2D image recognition developments. 3D point clouds do not have a regular format like pixels. The convolution mechanism does not always provide good outcomes. The point cloud domain do not have de facto standard dataset, such as ImageNet in 2D image recognition. Therefore, standard method for 3D object recognition is to learn the network from scratch. The answer is the lack of large-scale 3D datasets suitable for pre-training such as ImageNet in image recognition. All 3D dataset scales are small compared to ImageNet because the construction of a 3D dataset requires a huge amount of effort compared to the construction of an image dataset. Therefore, there is not a large-scale 3D dataset for 3D object recognition by using point cloud in 2022. Therefore, in this research, we will challenge to automatically generate a 3D fractal model and a 3D fractal scene by focusing on the formula-driven supervised learning. Our research goal is to replace a human annotated dataset in the context of pre-training without any natural images and human labels. There are three key points in this research. First, automatically construct a point cloud fractal database, PCFractalDB, based on fractal geometry. Second, our approach generates 3D fractal models, a 3D fractal scene without human effort. Last, our approach achieved better performance than conventional self-supervised learning. We adopt 3D IFS, which is an extension to IFS, as a formula for the automatic rendering of 3D fractal models. In the first step, 3D IFS is determined by randomly initializing each parameter. The second step is the affine transformation based on the 3D IFS. In the third step, the fractal categories are defined based on the variance threshold. By setting the variance threshold, we expect to generate a clear fractal geometric structure in 3D space and expand the differences between fractal categories. Thereafter, the procedure's first step to fourth step is iterated until the end category is reached. In order to assist the increase in the 3D fractal model, we propose the fractal noise mix for instance augmentation inspired by point mixup. We automatically generate 3D fractal scenes that include 3D boxes by considering their scale, position, and orientation. We evaluate the proposed method by pre-training the point cloud fractal database and fine-tuning it with ScanNet2 and SUNRGBD. This is Table 11 in the main paper. We compare the baseline methods and our PCFractalDB pre-trained model. Moreover, the performance of PCFractalDB is relatively higher than that of previous state-of-the-art self-supervised learning methods. This is Figure 1 in the main paper. Of particular note, we found that the proposed method achieves the highest results for 3D object detection pre-training in limited point cloud data. For example, in 10% of training data on ScanNet v2, the PCFractalDB pre-trained VoteNet performs at 38.3%, which is plus 14.8% higher accuracy than CSC. In conclusion, we could confirm the effectiveness of the point cloud fractal database as a pre-training in 3D object detection. You can access the source code for point cloud fractal database on GitHub. Thank you for watching.